Okay. Right, so the equivalent of electrostatics, so we had electrostatics, if you remember. Kind of hot in here. Electrostatics is charges not allowed to move. Right? But for magnetostatics, which is what we're going to be dealing with until chapter 7, and I think chapter 7 is only electrodynamics, it's not magnetodynamics, is currents not allowed to change with time, right? Okay, and that's called steady. Let's go. Steady currents. Okay, that's what we're going to be dealing with in this chapter, chapter 5, steady currents. Okay. Okay. So basically we think of current as a continuous flow that started infinity in the past and will continue to infinity in the future, right? Because there was no time where it ramped up to a certain value, right? It's always been there. Got it? And it's the same everywhere, right? There's no charge piling up anywhere. Okay. So perfectly steady currents actually don't exist, as opposed to static charges, which do exist, right? But perfectly steady currents don't really exist because you've got to turn them on, right? They got to come on at some point. But we will use, magnetostatics is actually a pretty good approximation, even for things like your, household currents, which alternate at 60 hertz, which is strange, right? Because it's like the current is changing direction 60 times a second. And we even use magnetostatics to deal with that. So we are, it's a pretty good approximation for a lot of stuff, right? So when we see things like induction, that's really in electrodynamics. You can use induction voltmeters in your house, current meters in your house. Have you ever done those? Ever seen those? They'll wrap around a wire like this and tell you if you've got current flowing. Yeah. So now note also that if you had a charge moving down the line, if you just had a charge moving by you, right? We don't call that a steady current. Can you tell why? I mean, well, okay. Is it the same everywhere? Is that what you mean? It's not the same everywhere?
Yeah.
Yeah, because it's here and then it passes you and it's no longer here and it's over here now, right? It's not a steady current. Okay. Okay, and when a steady current is flowing down a wire, you can say that the magnitude of that current is the same everywhere, right? Okay, so just be clear what that means. So what that means in general, right? If we think about our continuity equation, so remember we had the continuity equation was, so let me write this a different color. So continuity equation, we ended with this on Tuesday, was del dot J. Remember, J is the volume current density is equal to negative partial rho partial T, which means that any current, the divergence of the current has to be due to some change in the charge density somewhere, right? But if you have a steady current, this is always zero. So steady currents, there's no charge buildup anywhere. Partial rho, partial T equals 0. Therefore, del dot J equals 0, right? Okay. So now we're ready to say, if we have a steady current somewhere, how do we get the magnetic field that's generated by that, right? Because currents are generators of magnetic field, just like charges are generators of electric field, right? Okay. And we have something that you may have not seen in 116. I am really not sure if you ever see this in 116. It's called the Biot-Savart law. Does that sound? Okay, so you do see it. Okay. It's just going to look a little different here because we're a little more formal, right? Okay. All right, so let's go on to that. All right, so the way that we can get, it's a general form that we can use for line currents. So that just means like current on a wire or something, or surface currents or volume currents, right? We can use it for any of those things. Okay. And it's called the Biot-Savart law. Okay. And let's kind of set this up a little bit. Let's look at a coordinate system. Oh, maybe that's a little too big. Hold on, let me move this. I'm gonna move this down a little bit. And let's have a current, a steady current going around some loop. This is a line current, right? So I'm not going to draw any pictures for the other ones, but it's going to be a generalization. So we're going to look at a line current here. There's current flowing around a steady current, that is, flowing around this loop of wire. And again, we have our coordinate system that we're used to, right? So we have a field point that we're interested in. Okay, so let's say that field point is out here, P. We want to know, what does the magnetic field do to this current loop at P, right? So that means when I draw a vector from the origin to P, what do I call that vector, guys? R. R, exactly. That's R, just like before, right? Now, let's look at a little tiny element of current, right? And so that would be, we can represent that by, you know, IDL. So I'm going to draw a little DL, maybe here, it's a little easier to draw. It's tangent to the curve, DL prime, okay? And DL prime, we always write, is I DL, right? Sometimes we put the vector nature on the DL, sometimes on the I. Okay. Okay. So when I draw a vector 2, let's see, I'll do that maybe in green. When I draw a vector 2, that where that little DL is, where the little current element is, DL prime, sorry. What is that vector? R prime, indeed. Okay, it's really hard to see, I'm sorry. And then, of course, when we go from the field, from the current element to the field point, what is that vector called? Omega, or script R in your text. This is just exactly analysis, except for pointing to little bits of current as we go around the loop, right? Make sense? Okay. Notice that the current vector, the magnitude of the current is same everywhere, has to be steady currents. But the direction of a, you know, a current vector is changing as you move around that loop, right? Okay. All right. So then Biot-Savart law looks like this. B at your field point is mu naught over 4 pi. And nobody actually has like a little constant that they call that. Remember how we had 1 over 4 pi epsilon naught was K? Nobody actually uses a little constant for this. I don't know why, but they just don't. So I'm not going to either. So mu 0 is that permittivity of free space. You might have remembered that from 116. Oh, sorry, not permittivity, permeability. And it's equal to 4 pi times 10 to the minus 7. And it's newtons per ampere squared. Okay. All right. And then we have an integral. And in this case, it's a line integral because we here are just dealing with the a line current, right? And so it's I cross omega hat over omega squared. Okay, again, goes as 1 over omega squared, dl prime. And here that dl is not a vector, right? It's just the dl. Now, I is just, it's constant, right? The dl, if I make dl prime a vector, it will tell me the direction of the current, but the I itself, right? The current value everywhere in that loop is, so if you measure the current everywhere, you get the same number, right? So there's no reason I can't pull it out of the integral. And I'm going to use my dl as a vector, right? And I'm going to put it there in the cross product instead. So it's a little weird, but this is what people like to do. And I think it does help with calculations. Okay, so bring I out of the integral and make this dl prime a vector, because it just changes directions. That's all it does as you go around the loop. Right? Okay. Does this make sense? Sort of? So the integration is along the current path in the direction of flow, right? Make sense to you? Yes? I hope. All right, and then the units of B are newtons per ampere meter, which is a Tesla. Anyone have an idea what the Earth's magnetic field is in Tesla? So what do you think is 1 Tesla a big field or small field?
Huge.
It's pretty big, right? So what's your guess for the Earth's magnetic field? Millitesla, smaller or bigger?
It has to be less than a Tesla.
Definitely less than a Tesla. Yeah. Yeah.
So it sounds too little.
Yeah. Oh, really?
That's about right.
So let me tell you that most MRI machines are like maybe 1.5 Tesla, 2 Tesla. And they're pulling chairs in.
I'm gonna say micro Tesla.
Micro Tesla, that's right. 57 around 57 micro Tesla, right? Yeah, Teslas are big. It's not the best unit in a lot of ways. What do you think the biggest magnetic field we've created on Earth is? Like man-made.
I'm gonna say 15 Teslas.
So we've actually done better than that. 45. Yeah, yeah, yeah. Huh? It's like it's some physics facility where they, yeah, it's just huge fields. When I was in grad school, I went to, I stayed at Brookhaven National Lab for a couple months doing an experiment, and they were doing a high energy experiment, and they used these really strong magnets to curve the you know, the particles around, right? And so we had to map this, so it's big electromagnet, right? And there's 2 big giant plates, like the size of like 4 of these things these things put together. And you had to crawl inside and measure the field, go in there with a Hall magnetometer and measure the field. That's fun. You couldn't wear any, you know, you can't have any metal inside your body or, you know, on your clothing or anything like that. And it was a very interesting experience. And I don't think that we would do this. This was 1995 or something. So like, I don't think we'd put humans in there again. But it's like graduate students. They're like, yeah, stick the graduate students in the magnets. Yeah. It wasn't anywhere near a Tesla, but it was big magnet, right? Yeah. It wasn't like micro Tesla. It was like, you know, close to a Tesla. So that's why you couldn't have anything metal in there. Yeah. Anyway, that was fun. But we had these aluminum plates, these little aluminum plates that people just bring in there for fun, because aluminum is not magnetic. And you could, if you moved the plates, if you just like move them around, you could feel the forces from the eddy currents because it would actually set up a current, which would set up a magnetic field, which would react, and it would be hard to move the plates. We thought it was fun, even though we were probably hurting ourselves. I don't know how much evidence there is that magnetic fields of that size are bad for you, but you know, who knows? They do, but it's, you know, pretty short time. We were in there for like 6 hours or something, like a couple of times. Yeah. Yeah, explains a lot. No, I'm just kidding. Yeah. Fun. All right, I think we should do an example. And I'm going to show you a method that I like to call the pedantic method. For setting stuff up. Okay. It requires less thinking in a lot of ways, which can be good, right? Until you build your intuition, and then because it's kind of hard to set all this up, even for a simple problem. Okay, so let's do an example, and then I'll see if you guys want to try your own. Okay, let's do an example. We're gonna find magnetic field a distance s from an infinite straight wire carrying a steady current. Oops, carrying steady current I. Okay. All right, so let's look at the setup. So here's our wire, let's say, and let's let the x-axis be along this wire. And we want a distance s above, okay? So I'm just going to put it up here. This is our field point. Actually, we had that in some other color now. I forgot what color it was, but anyway, I think it's this. This is our field point. And we might as well orient the z-axis along that point, right? Here, how about if I draw my wire in pink here? So this is the wire, it keeps going, but that's the x-axis, right? My computer's doing its thing again. Okay, let's see. Okay, we're at 95%, so we should probably make it. Okay. All right, and then, so this is the x-axis coming out this way. And then we have the z-axis. Okay. And then we'll have the y-axis kind of coming in and out like this, right? So we have the plus y-axis and the negative y-axis here, okay? That makes sense? Okay, and now we've got to set everything up. Okay. We want to do the Biot-Savart law, so I'll write that down. So B of R is equal to mu 0I over 4 pi. And then we want this DL prime crossed into omega hat over omega squared. Okay. Notice that the vector nature of the magnetic field comes from the cross product, which of course is also a vector, right? As you all know. Okay, so the pedantic approach is to just use the coordinate system. Just use the coordinate system. All right, so let's define all of our vectors. So if we go from the origin, let's make a little DL out here. Or DL prime, sorry. Yeah. So there's a little element of current that we're going to point to. Okay. We have the field point P, so I know what R is going to be, right? So if I draw R, let's draw that in the blue too, I guess. This is R. Okay. Let's write down, I didn't write it down. There is a distance S. We're above the z-axis by distance S, right? That's what the problem said. Okay. If I'm going to write down the R vector, what is the R vector in terms of the coordinate, and the unit vectors, x hat, y hat, and z hat, what is it? Well, isn't this R here?
It's an S and a Z hat.
Yeah, it's S Z hat. Yeah. Okay, sorry, I should have put that down. Okay, fine, and let's look at R prime. So R prime is going to point from the origin to the field point here. Not field point, sorry, my bad. To the element of current, this is R prime. And what is R prime in terms of the coordinate system? Yep, it's something X hat. No. Remember that DL prime could move, right? Right, so I got to point at all the current elements, but I'm happening to point at one where? At what? Why would it be S? Maybe S is 3 meters. Why would I point at one at 3 meters? And even if I was pointed at 3 meters, is that the only place I could point it at a current element? No. How would you describe this point over here? Right here. I was pointing at. Look, how would you write down that vector? Well, okay, think about the point. What is the point? What's the y coordinate of the point?
See,
What's the z component of the point? It's just x hat. Exactly. Okay. This is going to be a function of x. Think about what you're going to integrate over, right? You have to go to each of the current elements all the way over there and all the way over the back of the other way, right? Okay, so this means that omega, the vector that we can draw here, that's going from the current element to the field point, it's bad color, sorry, omega. Well, I already know how to do omega, right? It's r minus r prime. Right? So this means that omega is, so we have S Z hat minus X hat. There's omega. Yeah? Okay. Now, I can get all the things, right? I can get the length of omega. I can get omega hat. Let's get omega hat. That's omega vector over the length of omega. Well, I don't need that. Those bars. It's implied. So, well, I guess I should get the length of omega first, right? Length of omega is going to be s squared, well, square root of s squared plus x squared, right? That's easy. Okay, over here, this is going to be s z hat minus x hat over square root of s squared plus x squared, right? That's what omega hat is. And now we're ready to go up here and think about what we need to do. Up here, we need to take a cross product. So we need one more thing, and that is, what is DL prime? What is DL prime? So I'll do that here. I'll just outline this guy in green. So what is DL prime? What direction is it in? X hat. So what is it? DX, that's right, DX X hat, right? Now I just got to do a cross product, and I'm just going to use the, the determinant way of doing that, right? So we have DL prime cross omega hat. And so to do that, I'm going to set up my X hat. Oops, sorry, it's supposed to be down. X hat, Y hat, Z hat. And then the first thing in the cross product is DL prime. And so it is DX in the X direction and 0 in the other two. And then my second thing is omega hat, which has a negative X over omega, right? Remember, this is omega here. This is the length. So it has the negative X in the x direction, it has 0 in the y direction, and it has s over omega in the z direction. Yeah. Okay. So basically we just have to do the cross product to figure out that top thing in the Biot-Savart law. So, okay, so for the first thing, we cross out these the first column and the first row. This gives me 0 times 0 times x hat, right? So it's 0 x hat. There's no x hat component. Okay. And I put a negative sign, and the next thing is negative sign y hat, and then I'm crossing out this row and this, and I get s over omega dx, but then the 0 times negative x, I don't get that, right? Nothing. And then plus z hat, and then I get, let's see, I'm crossing out this row, and I get 0 again. Yeah? So this is actually just negative s over omega dx in the y hat direction. Yeah? Okay, cool. Let's see if it makes sense from what we know from 116, right? So if you think about a current wire, right? So what do you usually do? What I always do is I have like, if you have a wire like this is how I get the magnetic field. I curl my hand around, right? And so coming at me this way is the negative y direction, right? Okay, that makes sense. Okay. So, and this is, we're going to integrate. So we've got to integrate, we got to figure out what we're integrating over, but let's just, I think we're done and we're ready to put it all together. Yeah. Okay. So I'm just going to duplicate this layer. Move out of the way, please. Okay, and then I'm going to erase some stuff. Okay, so we need this omega squared, which we know is here. And we need our cross product. All right, so let me just write it out here. So we have equal mu 0 I over 4 pi. And then the integral is going to be, let's see, the dl prime cross omega is negative s over omega, and then dx in the y hat direction. And then I have over omega squared. And so I really get omega cubed here, right? Good with that? Okay, the s is just a constant. That's not changing. And so I can rewrite to mu 0 I. I'll put the negative sign out here. I'll put the y hat out here too. And then s, let me write this better. Negative s mu 0 I y hat over 4 pi. And then the integral becomes dx over the square root of, oh, my bad, x, what was it again? Now I forgot. S squared plus, yeah, s squared plus x squared to the 3/2, right? Okay. And now the integral is from negative infinity to infinity. But notice that the integral, the integrand is an even function of x. So there's no reason why I can't just pull it, say like, oh, it's 2 times the integral from 0 to infinity, right? So that's nice. So this is going to be negative 2 times s times mu 0 times I over 4 pi in the y hat direction. And then the integral from 0 to infinity dx over s squared plus x squared to 3/2. Okay. And go look up that integral. I don't remember how to do those. Let me get a new layer and I'll erase some stuff. Okay, so this integral is, I'm gonna get, so let's see, how about if I do this? I'm gonna get rid of that 2. I'm gonna have s mu 0 over 2 pi and then I. And then I'm gonna put negative y hat here, just like that, just to be clear about that's the direction. And then this integral, which you could just go look up, is x over s squared, 1 over s squared plus x squared to the 1/2, evaluated between 0 and infinity. Okay. All right, so let's see. Hold on, something's funky. Hey, what happened? Can someone look up that integral for me real quick? I think I didn't write down the plus sign. There might have been a plus sign here. Or a minus sign. Just like a squared plus x squared to 3/2, 1 over that. Yeah. I didn't write it right down right.
X over a cubed times the square root of x squared over a squared plus one. You want to just look at it?
Yeah, let me see it. Oh, okay, yeah, so x squared plus a squared, integral, good. Yeah, it's this one. I think I did write it down. So this would be x over s squared, right? Times the square root. So I did write it down right. Okay. But it's not cubed, but. All right, now I gotta figure out what did I do next, because now it looks funky. Why does it look so funky? Okay, just give me a second. So I think what we can do, one is pull out the s squared, right? So we're gonna go, let's see, if we pull out the s squared, we get mu 0 I over 2 pi s, and we still have our negative y hat, right? And then I'm gonna pull out x squared from here, because it's really hard to evaluate at infinity yet, because like I have this 1 over x squared, and then I have an x, so I've got to do something about that, right? Do you know what I'm saying, right? It's hard to evaluate at infinity until you know actually how it goes, how the function goes. Does that make sense? Okay. This is the equivalent of what you probably have taught in calculus, where you take the highest power and you divide everything by the highest power. But anyway, it's the same thing. Okay, so I have x. Sorry, I just have x. And then I'm gonna pull out a 1 over, I'm pull out x squared from here. So I'm gonna get an x squared here, right? And then I get 1 over s squared over x squared plus 1. Yes? Everybody good with that? 0 to infinity. Then one more step here. I get mu 0 I over 2 pi. Thank you. Thank you. To the negative y hat, and, or sorry, times negative y hat, and then here we can have just 1 over x squared. Stop it. 1 over x squared, no, 1 over x, how about 1 over x, and then this 1 over s squared over x squared plus 1 to the 1/2. Yeah, good with that? All right, at infinity, what happens? What is that term? What do you think?
Goes to 0.
Goes to 0, indeed. So at infinity, it's 0. At 0, it doesn't matter at all. Remember, 1 to anything is fine. I just messed up by putting my parentheses in the wrong place. Yeah. Okay. All right. So this form is good for the infinity, right? This form is not great for the 0. The infinity, we get 0. Hope you agree, because it's 1 over, it goes as 1 over x when x goes to infinity. Right? Which is 0. Okay. So we know that at infinity it's 0, but here when we look at this form, when x is 0, I'm confusing myself. How am I getting it not being 0 for both terms? Well, no, then the whole thing would be 0, which is not true for a wire. Yeah, I'm confusing myself. All right, we got to figure this out. I think partially is just that it's too messy, right? So I can't figure out where I've gone wrong. Let's go to a new layer and figure it out. Okay. Fine. So we're sure because we looked up the integral, right? I'm just going to deal with the integral, not all the extra terms that we have. Okay. So we have x over s squared, 1 over s squared plus x squared to the 1/2 from 0 to infinity. Yeah. Okay. Oh,
You're using the anti-gravity factors.
I'm sorry, what?
You're using the anti-gravity maximum. Does it matter?
I don't know what you mean.
Like it computes the derivative like manually with integration and it does it with maxima too. It just puts it on different forms.
I don't think it matters at all. No, no. That form that I'm using is the same that I have in my notes. Yeah, and I'm sure if you looked it up on a different integral table, you get the same thing. Okay, I think I know what I did wrong. Okay, so let's process this. So let's do 2 things. We're gonna do for the infinity limit, we're gonna process this as we're gonna pull out that x squared, right? We do the same thing. So we have x over s squared. I don't even care if there's an s squared there, but I'm just gonna move it out. And then we have x, and then we have 1 over s squared over x squared plus 1 to the 1/2. And then, but it's over x, right? When we pull out x squared, it's a 1 to the 1/2. That was my mistake. And so this is 1 over s squared, and then 1 over s squared over x squared plus 1 to the 1/2. And when we do the limit at infinity, we get 1 over s squared. And then this term goes bye-bye. And you just get 1. You just get 1 over s squared. Yeah. For the 0 limit, right? You just get 0. Because x is 0. Yeah. Okay, so it's the infinity limit that gives us 1 over s squared. Okay, back to our mess. And let's get rid of this. Oh, I'm on the wrong layer. Just write down. All right, so from this point, we have b, and we're not going to say it, r, equals, and then this s will cancel out. So we have mu 0 I over 2 pi s, right? And in the negative y hat direction. Yeah? Make sense? So this is, but this is the result that maybe you remember from 116. Okay, okay, that was fun. All right, let's see, what is the time? Well, let's start you on an example on your own. And we shall see. Okay, I'm gonna set it up on the board up here. And probably it will get erased by tomorrow, but you may not finish. I don't want you to work on it at home. I want you to work on it in here with people, okay? But you're gonna try the pedantic approach. I think it's the best approach. But in this case, you're gonna want to work in cylindrical polar coordinates. Okay. Let me write it up. Huh?
Spare the battery.
Yeah, what I'll probably do is write the problem down on this for Isaac. And then it'll be in the recording and then I'll stop. So it doesn't like die, but it's probably okay because I started with a charge. The problem is when I don't have, when I come in here with like, 60%. All right, now you may not be able to see, so we're probably gonna have to turn on some lights and do what we do usually, so. Okay, so we're gonna have a current carrying loop, so it's a circle, okay? And so we're gonna draw our little DL prime, it would be, here. There's current carrying I. Okay, steady current. And the radius of the loop is R. Big R. Okay. And then, and this is the origin of the coordinate system, you might as well. And then you're looking for what is the B field up here at Z. Field point just defined by Z. Okay. That's what you're after. And recall that the Biot-Savart logic tells you cross, plus cross. Okay, now some hints here are to use cylindrical polar, right? And that DL prime. Remember, we have those little things that we know how to do, right? So DL prime, DL phi in the phi hat direction, right, is SD phi in the phi hat direction. Where phi is the angle that goes around here, right? Goes around the loop. Yeah, remember that? Okay. So you're gonna use this idea and then the pedantic approach to get your R prime, right? And then once you get that, you've got your omega. The other thing you're gonna need is that and I gotta move this to it. Right? The other thing you're gonna need is just to remember that you have like X is, R cosine of phi, Y is R sine of phi. Right? Yes. Yep. So that means also that S hat is cosine of phi X hat plus sine of phi Y hat. This should help you implement the pedantic approach. remember what S is? So maybe we should draw this DL somewhere else. It might be a little more helpful to draw it somewhere else. Because this is just the radius, but if I were over here, if I had a DL prime here. You know. The coordinate S is out, is the radius coordinate, right? That makes sense.
Yeah.
And S hat points in the direction of the radius coordinate. Okay. All right. Good luck. I'm gonna draw it on the board for Isaac and then I'll shut this thing down. Although it seems to have started to be quiet, that makes me suspicious. Oh, falling off. Work together, you know. Yeah. Okay, I'm shutting this down now.